All right, so let's get started. So at the end of the last lecture, I was saying, okay, we'll compute second moments. So and the easiest one to do this is in the k not all equal sat model. Everything's very symmetric. The expected value to the n 1 minus 2 to the minus k minus 1 to alpha n, the number of edges. And then if we want the second moment, we sort of have to sum over pairs of possible solutions and calculate the expected number of those that we have. And for a pair of configurations, the probability of them both being solutions depends on sort of how many variables they agree on. So we'll say gamma n is the number of variables they agree on, and then we can just sort of sum this over choices of gamma. If you were in Dylan's talk on yesterday, he did a very similar calculation. But the picture we'll get will be a little bit more complicated than the one he had, and that will that will be the reason for lots of difficulties. But and so I'll write expected value of z squared is equal to expected value of z times something exponential in, or e to the n to some function. And so I want to understand what this function looks like. So it's when gamma equals 0 and we have sort of looking at two completely identical solutions, then the contribution will just be the expected value of z. And so f should be 0 at gamma equals 0, and also at gamma equals 1, because it will be symmetric about a half. Then this function has sort of an entropy of alpha term in it. So the derivative at 0 will be infinite. So there'll always, like whatever the value of alpha is, it'll always be increasing at 0. When alpha equals 0, it's just the entropy function. For alpha up to this threshold, 2 to the minus k minus 1 times log k over k, it still looks more or less like a sort of unimodal function. But then when we get up to this threshold, it starts being decreasing, at least for a little while, and you start getting negative values. But there's always a little bump at the beginning because the derivative of the entropy function is infinite. So if you remember Dylan's talk yesterday, this was not what the picture looked like. In his picture, it was always you would have something that was decreasing at 0. Okay. So what this says is that what this sort of bump and then negative value says is that if you take a solution, typically there'll be exponentially many solutions close by. But if you go out to a sort of slightly bigger radius, then you'll typically find no solutions. So solutions come in clusters which have exponentially many solutions in them, but only a small radius. And when we're at this clustering threshold, this the length of this bump is about 1 over k. So the radius is quite small, at least if k is big. And then as we increase alpha, they get even smaller as you go. So this is sort of the picture up to about 2 to the k minus 1 times log 2, whereas this was 2 to the k minus 1 log k over k, so something much bigger. And as you increase alpha, these curves get sort of smaller and smaller. And at some point, the value at a half is sort of getting smaller and smaller, and at some point it stops becoming the maximum value. What we'd like is is if it stopped becoming the maximum value exactly at when it hit 0, because the value at 1/2, so expected value of z is equal to e to the n f of alpha 1/2. So we can only, so when the function here hits 0, that means that the expected value is, or like starts becoming, tending to 0, and then you don't expect the second moment method to work anymore. But it stops working a little bit before that. It stops working when this maximum becomes the same height as these maxima at the endpoints. And so as a result, if you do the second moment method, so there's essentially your computation of when you have solutions, there'll be an additive constant factor that you're off by. So if I write alpha 1 is the maximum alpha such that expected value of z is greater than or equal to 1, and alpha 2 equals the maximum alpha such that f of alpha 1/2 is equal to maximum over gamma f of alpha gamma. This is when the second moment method works. Then this is an upper bound on when we have solutions. This is a lower bound. They're both of this form, 2 to the minus k minus 1 log 2 minus a constant, but we'll get alpha 1 minus alpha 2 converging to some constant that's bigger than 0. So we will have a gap. And everything that we're sort of working towards is sort of trying to, not have a gap, have a sharp solution for, when we have solutions or not. And the real satisfiability threshold will be strictly between alpha 1 and alpha 2. Yeah.
So yesterday there was no epsilon k, I think, in the formula, on the left one. Below,
yeah. So this.
Should we think about it as being small?
Yeah. You should think of this as sort of epsilon k tending to 0 as k is tending to infinity.
And the c which is here is not the same as the c which we just wrote over there.
Right. Yeah. Yes.
So
Yeah. They're different. Yeah. Okay. Good. Any other questions? Okay. So.
Sorry.
Yes.
Maybe just remind me what the alpha was and what this model and this.
Yeah. So this was. Okay, so alpha times n is the number of constraints, and the model is one where so we have Boolean variables, sort of x1 up to xn that are either true or false, and we pick clauses that are like x2 or x7. Or not x11. And so for ksat, we would want these to be satisfied. For not all equal sat, we want this to be satisfied and it also to be satisfied when we plug in not x as well. So, or equivalently, we want, when we look at x2, x7, and not x11, we want at least one of them to be true and at least one of them to be false, hence they're not all equal. And then z is just the number of ways of assigning the Boolean variables so that all the constraints are satisfied. Okay, good. And yeah.
Maybe what's the f of alpha?
So then this is a formula for the second moment. We're summing over sort of pairs of solutions at distance gamma from each other. And so this is sort of the number of ways of choosing two solutions that are at distance gamma. 2 to the n for the first one, n choose gamma n for the second one. And then this is the probability that when you have two that are at distance gamma n from each other, that they're both satisfied. And then I just want to, And then I just want to sort of think of each of these terms in this expression as the expected value of z times e to the n times f of alpha gamma. And I just want to pick f alpha gamma so that this term is equal to this term. And then the second moment method is basically going to work if the maximum of f occurs at a half. Because if we have that, then we'll have expected value of z squared is about the same as the square of expected value of z. Good. Any other questions? Okay. So, and I should say, so this is sort of the, this one is the threshold for when we get clustering. And we can work out similar thresholds in other models as well. So if we were looking at K coloring, and again, I'm going to think of K as being big, then we would get clustering for D bigger than 1 plus epsilon K, K log K. And in a moment, we'll see where this K log K is coming from. So why do you get clusters of solutions? Well, if I take a random solution, some of the variables I could sort of flip between their values, either between true or false or blue and green, without upsetting any of the constraints. So they're not sort of forced by any of the constraints they're in to take a particular value. So we can think about this in terms of, what does the distribution look like locally? And we said that at least when the second moment method is working, the local weak limit of the configurations we get are these translation invariant Gibbs measures on the infinite deregular tree. So I want to sort of understand what local perturbations of those look like. So it's sort of, if I fix everything far away, what can I, so I have the tree, I fix my configuration a long way away. What can I say about what's happening at the root, in a neighborhood of the root? And this is what's called the reconstruction problem. And the idea is, so I'll take mu, a Gibbs measure, on the infinite deregular tree. And usually I'll think mu will be one of these translation invariant ones. And then I ask, okay, well, under mu, what's the probability of seeing some configuration at the root, given the boundary, given the configuration that I see at level L? So because the spins at level L are random, this is a random variable. And we say that the reconstruction problem is not solvable if this converges just to the marginal probability as L tends to infinity. So essentially, and this is equivalent to saying that as L tends to infinity, you have no information left about the value of the root. It's equivalent to the measure being sort of tail trivial. It's also equivalent to, and I won't show this, but it's in the notes. It's equivalent to mu being an extremal Gibbs measure, meaning that you can't write it as a convex combination of other Gibbs measures. Yeah.
The clean coloring, for instance, if the instances are planar graphs, does it change the expression?
Definitely, yeah. So, so this is really for random graphs. If you know, planar graphs, you'll generally have to have lots of small cycles. And so it won't be locally tree-like. And I mean, you know, if you're if your planar graph was the lattice, you would have much more sort of rigidity. But yeah, so so this story is very much a random graph specific one. I mean, there are models of random planar graphs, and yeah, you should, I guess, ask the people who work on random planar graphs. I mean, and you know, they do look at spin systems on these, and there are sort of computations that you can do with that. But I think we'll get sort of quite a different story. That, yeah.
So if it's a planar graph, then you can always color it with 4 colors or 5 colors?
Indeed, yeah.
So that's making another difference?
Yeah, absolutely, yeah. Yeah, so in terms of the colorability threshold, as soon as K is at least 4, then there'll always be colorings, of course, yeah. Good. Any other questions? Okay, so yeah, so the idea is, you know, you look at the you look at the spins far away and try and guess what the root is. I mean, you can. So this is, you know, you can imagine, you know, if this was sort of like some evolutionary history, you start off with, you know, Adam and Eve at the beginning, and you see everyone's family tree, and you see what that sort of mutates over time, and then we take, you know, everyone's, you know, DNA here, and you want to work back and work out what the original one was. And whether or not you could do that should like depend on like the mutation rate. And so we want to sort of understand when knowing sort of far away things gives you information about the root, because that will turn out to be sort of the very close, well, the same as sort of when you start having clusterings of solutions, because it's sort of saying that, you know, the spin at one location really depends in a sort of on the ones that far away. Okay, so we take this conditional probability, and it's by the Markov property, it's the same as sort of conditioning on everything below level L. So then, as we let L tend to infinity, we're conditioning on less and less information. So this is a backwards martingale. So it converges almost surely. And so we just want to know, does that converge to a deterministic limit? And so the distribution is converging. And how could we calculate it? Well, we have some boundary condition here. So I could write ML UV as sort of the BP messages when I fix a boundary condition at level L. And because the distribution in A converges as L tends to infinity, these messages must converge as L tends to infinity as well. So associated with a random instance of this, you know, coloring or you know, random sort of configuration given by this measure mu, then we converge to a possibly random set of messages. And we say the reconstruction problem is not solvable if they're deterministic, and it's solvable, meaning we have some information from far away, if they're not, you know, if there's still some randomness in there. Okay, and you know, there's no general theory for like when it's solvable or not. starting from the root, on each ray going off to infinity, if I look at the spins along that, then that's a Markov chain, and will generally be an ergodic Markov chain. So in each particular ray, you have sort of less and less information about the root, and it decays exponentially. On the other hand, the number of rays you have is growing exponentially. So these two things are competing with each other, and you want to know, which wins in the competition. Okay, so we could look at a couple of examples. One would be the easing model. In this case, if we look at the Markov chain, it will look like theta, and where theta equals tangent of beta. So this means as you go from a parent to a child, you have a half plus a half theta chance of it being the same, and a half minus a half theta of it being different. The eigenvalues are 1 and theta. Or we could look at the coloring model. And then, well, for a coloring model with the free measure, okay, you can't have the same value as your parent, and all of the other ones are equally likely. So 1 on k minus 1. Here the eigenvalues are 1, and all the rest are minus 1 over k minus 1. And so, if you think, like in a Markov chain, the sort of amount of information you have about your starting state over a long period of time is given by like the second largest eigenvalue in absolute value. And so you might expect that sort of plays an important role in this story as well. And so it does. So if theta equals the max over I greater than or equal to 2 of lambda, so if lambda I are the eigenvalues and lambda 1 is the biggest one, which is 1, and theta is the second biggest one in absolute value, then the Kesten-Stigum bound says that you have reconstruction if d minus 1 times theta squared is bigger than 1. Okay, so, and in this case, it's enough to just sort of look at level L, say how many you have in each state, and guess based on that. So in the case of the easing model, you would take all the vertices in level L, just sum them up, and how would you guess the state of the root? Well, if this was positive, you would guess that it started with a plus. If it was negative, you would guess that it started with a minus. And you can ask, when is this guess a good guess? Like one that's right with probability, more than a half in the limit. And so it turns out that if I look at the distribution of this, when d minus 1 theta squared is less than 1, then it just converges to a centered Gaussian, like when you normalize it. And you have no information left in the limit. Just if you just looked at this statistic, which is sort of the number of the sum of the spins on level L. On the other hand, when we're above the Kestenstiegen bound, you'll get some non-Gaussian limit. It might not look, bimodal, but you get something non-Gaussian, and it's more likely to be on the plus side if you started with a plus on the root, and more likely to be a minus if you started on the minus on the root. So Kesten and Stigum weren't studying the reconstruction problem exactly. They were studying sort of multi-type branching processes. And you can think of like this is really a sort of multi-type, like if you branching process where the spin of a vertex is just its type. And yeah. Okay, so this is what you would do in the Ising model. In the for this also holds for general Markov models on trees. And then rather than taking the sum of the spins, you would sort of first project it to the second eigenvalue of the Markov chain and then sum that up. And again, you would get sort of this dichotomy in terms of convergence to a normal versus a non-normal distribution. And if you have this property, then there is some information in the limit. For the Ising model, the computation is sort of, this direction is fairly straightforward, because if I condition on the root to be a plus, the expected value of a vertex in level L, you can check is just theta to the L, and there's d minus 1 to the L number of vertices there. So this is sort of like how much I shift the mean by conditioning on the root to be a plus. And if you look at the variance, so this is like summing over pairs of vertices in level L. Their mean 0, so it's expected value of sigma u sigma v. And this will just be, this expectation will just be theta to the power of their distance. So it's just sort of computing how many pairs there are at each distance. So d minus 1 to the L. So d minus 1 theta to the 2. And when d minus 1 theta squared is bigger than 1, then the biggest contribution from this sum is for big L, which means sort of vertices that are far away. Whereas when d minus 1 theta squared is less than 1, the biggest contribution to the variance is just coming from the pairs at distance 0. So this is sort of equal to a constant times d minus 1 theta to the 2L, which is the square of the expectation. So the sort of signal and the noise are square root of the standard deviation, and this expected value are on the same size, and so you can sort of, so you have enough information. So you do have some information in the limit. Going in the other direction is more complicated, showing, but it's a theorem that for the Ising model, you have non-reconstruction if d minus 1 theta squared is less than or equal to 1. And this is origin. Oh, okay. I've thrown out the page where I had the. This is why. Blur it out. From about the mid-90s. So, okay. There's a proof of this in the notes. You could conjecture that that the Kessen-Stigin bound is always the right thing to look at. And if your way of reconstructing the root is to just sort of add up how many of each spin you have at level L, it always is the right thing to look at. And so Yuval Perez, who was my advisor's advisor, did indeed conjecture that. And that was, so Elkanan Mosul, who was my advisor, that was his master's project, which he failed to do. And then for his PhD, he disproved it. So, so the theorem is that if you look at the, let's say the K-state Potts model, it's then Kesten-Stigin is not sharp when K is greater than or equal to 5. So in Elkanan's PhD, he proved this for K greater than or equal to 18. Then in my PhD, I proved it for K greater than or equal to 5. So it's really we're all working on the same thing, I guess. Okay. So conjecture, when K equals 3, it's sharp. And when K equals 4, it's also sharp when beta is greater than 0. And it's sharp when beta is less than 0 and when d is bigger than 33. So the K equals 3 case is known for d large enough, but not for small values of d. The K equals 4 case is Yontak Son has recently, but not finished writing it up, proved this again for d very large, and showed that when d is less than 32 and beta is negative, then the reconstruction problem is not sharp in that case. Okay. So, yeah, so anyway, open problem. So that's for the Potts model. The coloring model, of course, is a special case of the Potts model when beta is negative, and I mean we take beta as negative as possible. So let's do that because that's one of our random constraint satisfaction problems. And it turns out that for colorings, you can do better than just so you know, the reconstruction problem is asking, can we guess the root with better than random chance? For the coloring model, you can do better than that. A lot of the time, you can work out exactly the value of the root if d is big enough.
Alan, before you go there, can you comment on what happens when KS is not sharp? Is it understood what is the threshold and why? No, it's not. I mean, in general, so it will be something in terms of a measure-valued recursion.
and we don't have a general theory for that. Yeah, so we can sort of say some things in the like when you let the degree become quite big, but yeah, generally no. Yeah, so the Kestenstiegen bound is sharp if you only look at do what's sometimes called census reconstruction, where you just look at how many spins you have at level L of each type. And it's also sharp if instead of giving you the spins at level L, I just give you a very noisy version of the spins at level L. And you can ask, well, for any level of noise, can you reconstruct the root? And then there again, the Kestenstiegen bound is the right thing to look at. But so essentially you can get sort of, so the Kestenstiegen bound is sort of what you get when you sort of perturb around sort of having sort of a very little amount of information. But there are non-trivial fixed points where you have a lot of information and you need sort of, a smaller degree than the Kestenstiegen bound would suggest you do.
Is there a sense in which these functions you would need to understand the lead are very complex? Like, for example, could you show that any finite degree polynomial, bounded degree polynomial, would also not be able to beat the Kestenstiegen bound?
That was a question that Elkanan asked last time I talked to him, and so Elkanan conjectures that they will sort of low-degree polynomials of the spins will not beat the Kestenstiegen bound. So yeah, okay, good exercise. Okay. Yeah, we've got until Saturday. It's yeah. Okay, so if it was at level 1. If we have 3 colors, let's say, and we see blue, green, blue here, then the root has to be red. So in this case, level L or level 1 would tell us exactly what the value of the root. And if it looked like red, blue, red, red. Now at level 2, well, from these two we couldn't exactly work out this one, but these two we could work out that this was a green, and these two we could work out that this was a blue. So therefore, we'd still have enough information to definitely tell that this was a red. So this is called a sort of freezing. So where we want to be able to exactly work out the state of the root. And so now imagine we have a lot of colors. So K is big. Then how many children do you need in order to be able to guess the state of the root? Well, this is like the coupon collector problem. So you have a color here. Each of the children are chosen uniformly from the k-1 possibilities. And so that says you should have about k log k number to be able to have a good chance of exactly reconstructing the value there. So if I write f of kl to be the probability, so I'll pick L samples from 1 to k, and fkl will be the probability that they all appear. And so the sort of coupon collector sort of theorem, I guess, would be to say that if you have 1 plus epsilon, k log k samples, then this converges to 1 as k goes to infinity. And if you only have 1 minus epsilon k log k number of samples, then this tends to 0. Okay. So now let's give ourselves a big enough degree, so slightly bigger than k log k. And I'll let PL be the probability that the root is frozen by level L. So when I look at the colorings L level down, I can exactly work out the value of the root. So P1 is just k minus 1, d minus 1. So I have d minus 1 children, and each of them a sample from k minus 1 colors, and I want them all to appear, and then I can exactly work it out. Okay, and I could do this recursively. So in level 2, each of these ones I can sort of evaluate with, exactly work out with probability P1. So in the next level, I'm seeing a binomial number. And so this would be, say, greater than or equal to the expected value of f k minus 1 binomial d minus 1 Pn. And yeah, so the number of so now I see a random number of samples. But basically, if Pn is greater than or equal to, let's say, 1 minus epsilon and 2, then this binomial d minus 1 Pn will sort of with high probability be at least 1 plus epsilon over 3 k log k. And so it's big enough to make f here very close to 1 most of the time. So we'll be able to sort of inductively show that, oh, sorry, I meant Pn plus 1. So like a recursion in Pn. And so inductively, you'll get that Pn is always greater than or equal to 1 minus epsilon over 2. Okay, as long as we're above 1 plus epsilon k log k. Okay, and you can and how does this compare with the Kestenstigen bound? So this would say d minus 1 times, and theta was 1 over k minus 1, so it's 1 over k minus 1 squared equals 1. So this would be telling us that the degree should be like order k squared. But actually it's just k log k. So much smaller than the Kestenstigen bound would predict. And it's because we're looking at we're sort of reconstructing the root in a sort of very structured way, a sort of recursive formula to calculate the root rather than just looking at, how many, in this, how many red, how many blue, how many green you have in that level. Okay. Any questions about that calculation? Okay. So if you do a more careful analysis of this,
we saw that it takes, if you just are looking for freezing, then you need like a much larger degree than if you were to do something smarter, is what you see. Because now it's k squared instead of k log k.
No. So if you're just looking at freezing, you need k log k. If you were just looking at sort of census reconstruction where you say how many there are in level L, then you would need like k minus 1 squared. But you could ask, can you do something better than just working out when you can exactly reconstruct the root? And so the theorem is that when k is large, at least, the threshold for freezing, if you do this more carefully, you'll get k times log k plus log k plus 1 plus some epsilon k tending to 0. The threshold for reconstruction is less than or equal to minus delta plus epsilon k. So this delta is like some fixed number. So you can do reconstruction even for a slightly smaller values, but not much smaller. One minus log 2 plus epsilon k. So if you just decrease this like third order term from 1 to 1 minus log 2, then you can no longer reconstruct with any algorithm. But it does say that there's a narrow band in which you can reconstruct the root, but you can't, but your probability of exactly knowing what it is tending to 0. Okay. And now remember I said that clustering was at sort of 1 plus epsilon k log k. So open problem. Is sort of the threshold for clustering equal to d reconstruction? Is it equal to d freezing? This is an upper bound, but we sort of only know the clustering up to some sort of error that's sort of so less precise than we know about these reconstruction and freezing thresholds. So the conjecture is that it should be the reconstruction one. So now if it is the reconstruction one, what that says is the following. When we have freezing, the sort of the sort of space is broken up into clusters, and most of these clusters are frozen in the sense that if you look at all of the colorings in this cluster, on most vertices, they're always the same color. So if you take a typical vertex that's blue in one coloring in this cluster, it will be blue in all of them. And then there'll just be a small fraction of vertices in which they can vary. On the other hand, if we're below the freezing threshold and we have clustering, then within the cluster, all of the variables should be able to vary and be blue some of the time, or like take each of the colors with some fraction of the time. And so the question is the sort of algorithmic threshold for when you can find colorings, say, D reconstruction or D freeze. And if you ask the physicists, they tend to say this one, and suggesting that there's sort of a very narrow regime in which the space of solutions splits up into clusters, but they're not frozen, and algorithms can find them. But even the existence of this regime where you have clusters but they're not frozen is an open problem. Yeah.
So could you repeat that sentence concerning if it is blue, then it is always blue?
Yeah.
Colors are symmetric. They don't quite.
So I mean, for each cluster, I could, take the list of colors and sort of permute them, switch reds with blues and blues with greens and so on, and then I'd get another set of solutions, but this would be a different cluster that's sort of disjoint and far away from that. But when we just look at the colorings within this cluster, it's very rigid. The most variables are always the same color. And if you want to, as you said, we could sort of make all the blue vertices red and all the red vertices blue, and we'd get another coloring. But that would sort of change a lot of vertices and move us to a different cluster. So each cluster should have k factorial sister clusters that just you get by permuting the colors. But if you forget about that sort of permutation, then sort of within this cluster it's very rigid. Most vertices will always be the same color. Does that?
So it's the equivalent to say that there are a few vertices, if I fix most of the cars, that there are a few ones which are still allowed to change.
Exactly, yeah.
Yes.
Yeah. So most of the so if we did this on the tree, most of the vertices are sort of fixed by infinity, but there'll be a few vertices where, maybe like if it's 3 colorings, all the neighbors are red, and so this one could switch between blue and green. And if you count sort of what fraction you should see, if D equals, let's say, 1 plus beta k log k, then the number, or like the fraction of, I'll call them free vertices, will be about D to the minus beta plus little o of, plus epsilon D, so something tending to 0. So most vertices will be fixed, but a small fraction will be allowed to change. But most of these ones that can change, they'll only have 2 options. You'll be able to switch between, say, blue and green, but not to red, because you'll have a sort of neighboring red variable that's forced and can never change. Yeah, Dylan?
So why don't you expect the reconstruction threshold to be like basically the SAT threshold?
Because, so...
I mean, that would tell you that like you're fixed by things far away, so then at that point you start getting like maybe contradictions.
Okay, so let's say at the freezing threshold, once you know that there's lots of variables that are fixed, anytime you add an edge between them, then all of the colorings in that cluster would disappear straight away. But you have exponentially many clusters, and so you need to add in, so you basically need to double the degree d in order to get rid of all of them, because the coloring threshold will be at about 2k log k. Good. Any other questions? So if you want to think about what this cluster looks like, sort of within a cluster, most of the variables are always blue or always green or always red, but occasionally you get, I should draw a better picture of this. So most of the variables are frozen. They're either always a blue or always a green or always a red. But then I get some which are sort of either blue or green or either red or green. And these are the free ones. And so I'd like to sort of think about the measure inside this cluster as being basically like a product measure over these free variables. So you can sort of, I can flip this between blue and green, I can flip this between red and green, and the frozen ones always stay the same. And that should sort of describe the distribution. But if I had sort of two neighboring vertices where this is blue and green and this is, let's say, blue and red, then there'd be some dependency between these sort of neighboring free variables. They can't both be blue. Okay. And this could be a problem because, the fraction of these variables is like d to the minus beta, but each of them are next to d vertices, so if you look at the free variables, they'll be supercritical. Okay. But this is somehow an unlikely case. You're much more likely to get sort of something that's next to yellow and orange. For each one, they'll be sort of, they'll have two possibilities. I mean, there are even rarer types where they have, more than two possibilities, but usually it will be two. And usually neighboring free variables will have a different set of possibilities. So we should only sort of really think of them as next to each other if their list of possible colors overlaps, and then there's a dependency between them. So here, these ones can't both be blue, but this one I can set to blue and green independently of whether I set this one to yellow or orange. So if I think about neighboring vertices, the free vertices that way, the picture looks like just very rare, a very low density of free variables, and sometimes they're sort of interact with each other, but these interactions are very subcritical. So we just get very small trees of free variables typically. So so we take the sort of connected components according to this rule, connecting free variables if their possible colors overlap, and these will just be sort of very subcritical, so they'll just be trees of free variables, typically very small. And so how many colorings are there in this whole cluster? Well, the frozen variables are always set, and then it's just for each of these trees of free variables, it's the number of ways of coloring them, and you multiply them all together, and that gives you the total number of colorings in the cluster. Okay. And how do we? Well, actually, any questions about that? So the idea is once we sort of fix one particular cluster, the internal structure is very simple. Most vertices are frozen, and then there's just most of the ones that are free and can change, they don't interact with each other. So it's close to a product measure, and it's a product measure over these trees. Yeah.
Are those three variables somehow associated with the leaves more likely than most within?
Oh, so I mean, ultimately, I want to do this on the I want to think of this on the deregular graph. So in that case, there's no leaves. So yeah, each vertex should have probability about d to the minus beta of being free. But and so you will get this sort of fraction of free variables. Pretty rare, but not, you know, there's enough that we can't just sort of forget about them. And it's sort of it's the fact that so if we take a random coloring, then there's about this many vertices that we can sort of switch colors between. And that's the reason why when we had this sort of second moment calculation, that we had this sort of bump here. This is corresponding to the numbers of ways we can sort of locally perturb the solution by sort of randomizing these free variables. Okay. Okay. I have quite a bit to do in the next half hour. But any questions about this before I? So this notion of a cluster of colorings is still like I've left it in a sort of fairly vague way. How can I make that into a sort of rigorous definition? Well, so if I have a coloring on the tree, I could define sort of what extremal. So when we're above the reconstruction threshold, the measure is not extremal, and we sort of broke it up into a set of extremal states by taking sort of the limit of the BP messages. This converge to some limiting set of BP messages. And we could do exactly the same thing on the graph. So we start off, so we have our coloring sigma. We start off with the initial messages from U to V being of X will just be indicator sigma U equals X. So this is basically, initially, a vertex just tells its neighbors, my probability of being X is just whether I'm X or not. And then you iterate this, and so ML plus 1 is BP of the messages ML. And because so on the tree, if we did this computation, if we iterated the belief propagation messages, they would converge to the the fixed values M, and locally the measure looks like the one on the tree, so these ones converge as well. So this will converge to some M from U to V, and that satisfy M from U to V, BP of U. That satisfy all the belief propagation equations. And so this set of equations is a constraint satisfaction problem. And this is our definition of what a cluster is. It's or it will be some fixed point of these equations that will sort of describe what the cluster looks like. And so, what the theory says is, rather than look at solution sigma, you look at clusters given by M that solve this, that are solutions to this random constraint satisfaction problem, and you count them in the same ways as we did before. And so you just, but we built up a sort of general theory for how to compute moments for spin systems and random constraint satisfaction problems. So we'll just apply it to the M's set. Okay, so I want to define a sort of.
Can you just explain how this definition should be interpreted as the pictures you draw where you have the space of states and you have these little bubbles? I mean,
Yeah.
It feels like this is a little bit of making the definition fit the method rather than the question.
Okay. So what will these? So if we have a vertex U here that's frozen, when I iterate the BP messages, it will always just keep telling its neighbors, I'm definitely blue. So the frozen variables in the cluster will be ones that this message is just sort of one on one of the states and 0 on the other. And so you can, and actually really that's enough to define the cluster, sort of labeling, taking the frozen variables and sort of them telling their neighbors that they're frozen, and that sort of gives you a rigid structure for the cluster, and then around the sort of non-frozen ones, there's sort of the frozen ones give a sort of boundary condition to that, which will tell it what possibilities it can have. So you can, so these messages would encode which ones are frozen, which ones are free. For the free ones, what choices they have between the different colors. And yeah, I don't, so I don't know how much, if that answers your question or. Okay.
If you wrote before open question, is the clustering transition here or here, but it could depend on how you define your clusters.
Indeed. Yeah. So one definition of clusters would just be connected components of colorings.
That makes more sense.
Yeah. That makes a lot more sense. Not as tractable to work with though. But if I find clusters that look like, if I find clusters in this sense, then it sort of defines a set of, it defines something that will be roughly a connected component of colorings, because it will sort of tell me, okay, these are the ones that can be, within this connected set. These ones always have to be blue. These ones always have to be green. And then I can the free ones I can flip between, say, blue and green, or red and orange, and so on. So it defines a set of colorings that will be not next to, at least at a small, at least not neighboring any other colorings in the graph. Okay.
Sorry?
Yeah.
Connected components is like you can switch it from one color to another?
Exactly, yeah. So you're thinking of two colorings as being adjacent if they just differ at, say, one vertex, and then take the connected component based on that. Yeah.
So I think the process is very similar to the reconstruction threshold.
Yep.
Yeah. So I just wonder. So if that's they are actually same if it works on trace and because of the maybe they are exist cycles, so they becomes different.
There definitely are cycles in the graph, but sort of essentially, like at least in most neighborhoods of the graph, when I do this iteration, it will sort of stop changing before you notice that you're not a tree. Yeah, so that's sort of the idea, that it's enough to be locally tree-like. Okay. So, any other questions? Okay. So now I want to sort of, count clusters, and also according to their size. So let me just sort of write things by. So if we have a spin system, our configurations were sort of assignments of things in our set of possible spins to each of the vertices. Now in our sort of cluster CSP, our configurations are these sets of messages, and they live on each edge. The message is a probability distribution over X, and we have one of these for each directed edge in the graph. Okay. Then we looked at sort of empirical distributions on the set of spins, and this was essentially probability distributions over pairs of spins here. In the cluster case, I'll need a little bit more information. Around each vertex, there'll be sort of D incoming messages, and I want to know the joint distribution the joint distribution of seeing any set of them. And so I'll write LM as the sort of empirical distribution around a vertex of seeing M1 up to MD. So this is, L of M will be a probability distribution over D tuples of probability distributions. Okay. So how did we proceed to work out sort of like the moments of the numbers of solutions of a spin system? We went over all the empirical distributions and found out which one gave us the sort of biggest contribution. And in order to do that, we solved the BP equations. We said, okay, if we have sort of some trees, and then which have marginal probabilities on the roots, and they're independent, and then we add another vertex and connect them up, what is the probability here? And so this was a recursion that was exactly the belief propagation equations. Now, rather than having a spin at each vertex, we'll have a message at each vertex. And then we'll have a distribution over these. So I'll let S be a probability distribution over messages. So So it's a probability distribution over probability distributions. And, and the belief BP for sort of our S is called survey propagation. And the equation is, okay, so if I have a mess, if on each of these trees I have a measure, you know, S1 over M1, S2 over M2, and so on, then the survey propagation of up to SD minus 1 of set A will be some normalizing constant yeah.
Sorry, what's the word? Survey?
Survey, yeah, yeah, sorry. Survey propagation. MI. So this is exactly the same as if we were doing the belief propagation equations. We sort of have some trees. On each one of these, we have a measure on the message here. Then we add in a new vertex. There'll be a unique message that you can have at the root. It's you know, for spin systems, you can have, you know, spins at each of these ones, and then there's different possibilities you can have at the root. With the messages, there's only one thing you can have. Just this was M1, M2, and so on. This would just be BP of M2 and so on. And there's some reweighting that of the graph when we sort of weight by the change in the partition function when we add in this vertex. Okay, and then we'll, in order to find L that maximizes the empirical distribution, we want to find a solution S star is that solves the, you know, is a fixed point of this survey propagation equation. Now, by the way, I wrote this survey. The survey propagation equation looks more complicated than the belief propagation one. And that's because when we were looking at belief propagation, it was like these M's, they're measures over a finite set, so we can just think of them as vectors. And so belief propagation was a sort of equation that takes a set of vectors and gives you a vector out. So like M was a probability distribution over X. S is a probability distribution over this space, so it's a probability distribution over probability distribution. So we can't necessarily just think of that as a vector. And so we should think of this as a recursion of measures in general. Okay, but if we're in the sort of frozen state, most of our measures will be discrete. Most of the messages will be just saying, I'm definitely blue. A smaller fraction will say, well, I'm either blue or green with probability a half. And there'll be countably many possibilities, but we could still think of it as a sort of function of a countable number of states rather than a measure. Okay, and so we solve the equation S star, these survey propagation equations. And then, okay, and then for each empirical distribution H, we said, well, there's some contribution to the partition function of those. We had a formula for this in terms of the entropy of H and the weights, and then we wanted to, and then the overall limiting of log of 1 over n log of the expected value was given by the maximum over H of phi of H. So we can, just do the analog of that. We'll take psi L as the contribution of messages that have empirical distribution L, and then take the maximum over L of chi L, and the maximizer of this will be one that's given by the solution of the survey propagation equations, and so if L is the empirical distribution given by the survey propagation equations, then this optimal one, or the L star, will have a formula of the same form as we had before, where you just sort of work out the effect of adding in an extra vertex to the graph minus d over 2, the effect of adding in an extra edge to the graph. So MD. So this is the vertex term, and then minus d over 2 phi edge. And then this is the prediction for the expected size of the partition function, and so this is clusters weighted by and this is for counting clusters with weights according to what the number of colorings there is in the cluster, or their contribution to the partition function. Yes?
Is there a meaning in the thing called survey propagation? To review what's going on later on? No. Because it's a distribution of so you said that for clusters, the support of these measures would be very small, right?
Yes.
You would not have many options because you don't have that much freedom.
Yeah, it was called survey propagation because sort of like a simplified version of the messages along those lines were called surveys. And yeah, but I can't exactly remember why they use that term. Or no. Yeah.
So I think this equation only works when the configuration is not sensitive to a boundary condition. As you proved several days ago.
Not sensitive to a boundary. What boundary condition do you mean? Okay, yeah. So I showed a while ago that if when you have the uniqueness threshold, you would get a threshold like this. But also we showed a day or two after that if we wanted, that the expected value, so that was if there was sort of like a unique Gibbs measure and a unique solution to the BP equations. But we also showed that if we take log of expected value of z, then this is given by something of this form where this is given where you choose some BP fixed point. And so, yeah, and so here there can be, multiple survey propagation fixed points, and you would choose the one that gives you the biggest value of this expression. And that will give you the expected number. Okay. I have either -1 minute or 4 minutes because I started 5 minutes late. Let me just write down one more thing, which is and so by the way, if we're doing this, we should have, unless we've made a mistake, these should be equal because they're both, this is counting, essentially, like in the colorings case, this would be just the 1/n expected value of log of the number of colorings. And this one should be expected 1/n log of expected value of sum over clusters of the number of colorings in that cluster. But if I add up all the clusters and the number of colorings in them, that should just be the total number of colorings. But actually, given M, like a cluster, how do I work out its size? So Wm is its size of cluster M. Well, basically, we can just write it as sum over V by V of V sum over E by E. So this is just the formula that we would get if the graph was a tree. But the graph is not a tree, so why can this formula still work? It still works because if we because there's no contribution from the frozen variables, and the free variables should come in trees that are independent of each other. So this formula would also work if I had a disconnected set of trees. Just like the number of ways to color a collection of trees is just the product of the numbers of ways of coloring each of the individual trees. So if you multiply it all together, this is the number that you should get. And all right, psi m is 1/n. Just normalize this, and we can also think of psi as being just a function of the empirical distribution of m. Okay, so the last thing I want to write down is we can okay. I'll try and do it in this narrow space here. So this is a function of d. Phi, this is 1 over n log of the expected value, is some decreasing function. You can calculate that. So this is a function of d. I could also write down psi of L of S star. So this is the size of clusters whose empirical distribution is given by the fixed point of the survey propagation equations. And you should think of this as just the size of a typical cluster. So if I choose a random solution, look at its cluster should be e to the n times this. And so if we can find S, then we can find the associated empirical distribution, and we can plug it into this formula, and we could evaluate this. It only makes sense once we're, say, above the freezing threshold here, and it will be decreasing as well, and it will look something like this. So there will be a point here where the size of a typical cluster becomes bigger than the total number of solutions. And that should set off alarm bells. This is the condensation threshold. This is the point at which, if the model stops being replica symmetric and more complicated things start happening. And so on Saturday morning, we'll be we'll be sort of working on what happens when we're above this threshold, and and seeing what calculations you can do with this BP message view of clusters. And I'll, this looks sort of abstract, but I'll, when we specialize it to, say, colorings and independent sets, it will, these equations will be more concrete looking. Okay, so we should go to lunch now. Yeah.